Hello, everyone. Welcome to the first GGS webinar of 2025. This is very exciting. We've got a lot of different webinars planned this year at GGS. As you'll see, some of them are free, some of them are paid. You can find out about all our webinars on our website. But on to today's topic. I'm about to introduce Simon to everybody. But today Simon's going to look at Geology 101 for ground gas professionals, thinking about the science behind ground gas and how it's all working. So that's very exciting. And I'll hand over to Simon now, and enjoy.
Thank you very much, Louis, and welcome to this first webinar of 2025. I'm going to, over the next 45-50 minutes, I'm going to share my screen. That's a good start, and take you through a program of, here we go. Hopefully you can all see that. I'm the founder and managing director.
Sorry, it's not showing just yet.
Oh, it's the same problem again.
Yeah.
Okay.
I'll stay here until it shows.
Okay, thank you, Louis. Just try this again. What is?
It was there for a second then.
There. How's that?
No, can't see that.
This is intriguing. Screen to share.
There, that's it. You can see that now.
You can.
Yes.
Good. Right. So I'll start again. How's that? Is that good?
Perfect.
Lovely. Okay. Sorry about that. Technical glitch, first webinar and all that. Okay. I'm Simon Talbot. I'm the founder and managing director of GGS. I am a professional geologist, and for my sins, I've been working as a geologist for over 40 years in a number of different roles, but for probably the last 25 years, I've focused on ground gas contamination issues. Over the next 45 minutes, I'm going to be talking about geology in its broadest sense. For those of you who are perhaps haven't trained as had training in geology, but are working in our sector. I am very happy to answer any questions you can raise. Please use the dialog box at the bottom of the screen, and Louis and I will go through those questions at the end of a presentation. So I'm going to go through this content, a brief introduction to the Earth as a living planet, looking at the main geological processes, looking at igneous, sedimentary, metamorphic rocks, and then going into a little bit more about sediments, because a lot of our work is associated with the near surface and the sedimentary soils that we encounter. Then diving into the more ground gas related issues about pathway permeability, ground gas migration, and finishing off with some comments about geological structures, conceptual site models, and migration pathways in a little bit more detail. So I don't distract you by my ugly face, I'm going to try and turn my video feed off. Just looking for that control, and it's not appearing to me. So uh, there we go. That's better. Right. So the first topic, introduction to Earth and as a living planet. And many of you will know that there's a number of different elements to the Earth, and it is very, very old. The universe as we know it is 14 billion years old. The Earth is, in comparison, relatively young, only 4.5 billion years. Life on Earth occurred as single-cell organisms about 4.1 billion years. But some of the latest significant events happened relatively recently, such as the last ice age, and that only ended about 11,000 years ago. So in terms of structure, we have a solid inner core of iron and nickel, which is at about 5,000 degrees centigrade. This is surrounded by a liquid outer core, which is again iron nickel, and this flows. It has convection within it, and that convection creates our magnetic field. Around that, we have the mantle, which is a semi-viscous fluid comprising silicate minerals. And then on top of that, we have the crust, the lithosphere, the part of the planet we live on. This comprises continental crust and oceanic crust, the continents and the oceans. And these are split up into plates. And these plates are mobile. They float on the mantle and move around by plate tectonics. And these plates are thicker under the continents and maybe up to 50, 60 kilometers thick. But over or under the oceans, the oceanic crust is much, much thinner. It may only be 10, 15 kilometers thick. And these plates are moved around by the convection currents within the mantle. So some key features are things like the mid-Atlantic ridge, where you've got a spreading zone, and then you have subduction zones where crust is being forced down under other plates. And a clear example of that would be the East Pacific subduction zone. So both of those locations I'm going to talk about in a little bit more detail in a moment. So one of the most active areas of plate tectonics is around the Pacific plate, the so-called Ring of Fire, which is ringed by areas of volcanic arcs, and there's over 25 active volcanoes around the Pacific. It also includes subduction zones such as the Marianas Trench, but also down the western seaboard of the United States. You also have transform faults, again seen in California, San Andreas Fault, and other spreading areas such as the Pacific Antarctic Ridge. So that's quite far away. What about the effects of plate tectonics closer to home? Well, here in the UK, we are very lucky to be living on a relatively stable continental plate, the Eurasian plate. But even this is subject to earthquakes. And this is a map showing the epicenters of earthquakes of greater than 2.5 on the Richter scale, as measured between 1979 and 2022. But even within that, in the last published record from BGS in 2021, there were 320 recorded earthquakes within the United Kingdom. But most of these were less than 2 on the Richter scale, measured as a local magnitude. And at less than 2, it is usually not felt by people. And these earthquakes occur because the crust is continually flexing, and you have movements along faults. As I said, less than 2, not usually felt by people. Above 3, you'll get rattling of windows, rocking of pictures, and some minor damage, such as cracked plaster. But in the UK, even though we are in a relatively benign location, occasionally we get greater scale earthquakes. And the largest recorded in recent years was on the Llyn Peninsula in North Wales, where we had a 5.4 scale earthquake in 1980. So that's talking about the movement of the plates, and we'll come back to that in a moment. Let's go back and think about geological time in a little bit more detail. And geological time is split into eons, eras, periods, and epochs. And this diagram shows the concertina of these from over that 4.5 billion years. And most of you will be very familiar with periods, things like the Silurian or Carboniferous or Jurassic, but that's actually a really small part of geological time. And those periods are only referring to one of the latest eons, the Phanerozoic. But we've had the Hadean, the Archean, and the Proterozoic eons, which have lasted billions of years. The Phanerozoic only refers to just over the last 500 million years. And then those periods are split into epochs. And we are living in the post-Pleistocene epoch. And some people have coined the phrase the Anthropocene, which is those sedimentary deposits which are being laid down, which contain anthropogenic materials such as microplastics. So going back to our main program, and let's look at geological processes. And the most dramatic, of course, are those igneous processes and eruptions, volcanic eruptions. And these are photos taken from Grindavik in Iceland in last year's mid-Atlantic ridge eruptions. And these eruptions are very dramatic in one sense, but relatively benign. It's iron-rich lava, which is heavy, it's fluid, molten, typically about 1200 degrees centigrade. And it flows to the surface and then flows down gradient in a very predictable way. Not very good if your house is in down gradient of the lava flow. But as you can see, you can actually walk up to these quite safely and get quite close to them. The problem comes when you have these lava flows overtaking habitations. And this sort of lava is also the cause of creating the large shield volcanoes in the Pacific, such as you see on Hawaii. And indeed, the last major Hawaiian eruption on Kilauea in 2017 is shown on Google Maps. Here's one of the villages, and over a number of days, this village was overwhelmed by flowing lava, and that lava field took several days to cover that area. At the other end of the scale, we have the other types of volcanic eruptions which occur above subduction zones. And here, one of the best examples was the Mount St. Helens stratovolcano eruption, which happened in the 1980s. And these volcanoes are created by a different source of molten rock. What we have here is light, viscous, quartz-rich lava, which contains large quantities of gases and ash. And if you think of, say, the western seaboard of the States and the Pacific plate, which comprises oceanic crust with a thick layer of sediments and seawater being pulled down under the Rockies, all that seawater converts to steam and gives rise to very explosive eruptions. So in 1980, Mount St. Helens erupted, and just over a 9-hour period, 57 people were killed, and 540 million tons of ash fell over an area of 57,000 square kilometers. Very, very disruptive, very destructive. So very different volcanic activity depending on where you are on the plate tectonics. More gradual are sedimentary processes, and one of the more dramatic sedimentary processes is glaciation. And this is a map of the British Isles under the last ice age. And this had a number of events of extension and retreat of the ice cap. But the greatest extent was about, as you see here, between 23,000 years ago and 27,000 years ago. And you can see the limit in South Wales and up into Yorkshire. A current day example of what the United Kingdom experienced can be seen in Greenland. This is the Greenland ice cap, where only the tops of the highest mountains stick out of the ice. The thing about glaciation is that ice cap is a viscous fluid, and over thousands of years it will grind out huge quantities of rock and deposit it as sediments into the valleys or at the snout of the glaciers. And what you'll get left with are jagged mountain peaks, which have been eroded by freeze-thaw processes above the top of the ice, and then U-shaped valleys which have been carved out by the grind of glaciers traveling down gradient. So this leads us on to the other key feature, and possibly the more significant sedimentary process, and that is weathering, erosion, and transportation. So take the Himalayas, for instance. The Himalayas are subject to glaciation in the higher mountains, but you also get heavy rainfall, and rainfall falls on the ground, on the mountains, and flows into rivers, and the rivers carry down sediment, uh, gravel, sand, silt, and clay, and also the meltwater from glaciers. And just making reference back to plate tectonics, the Himalayas are rising at about a centimetre a year as a consequence of plate tectonics. India is travelling north and colliding into the Asian plate, and that collision is thrusting up the Himalayan mountain range. So rivers carry the sediment, but it's actually the flood events, the storm events that actually give rise to a lot of the sedimentation. This is an aerial photograph of the River Usk in South Wales, and this was the scene under Storm Dennis in February 2020, and you can see the amount of sediment that the water is carrying, but importantly, depositing within the floodplain. Unfortunately, part of the town is built on the floodplain and subjected to the flood waters. And more recently, we've seen the same event happening in Greater Manchester, where I live, and just a couple of half a mile away from our office, we've had properties flooded out by the recent storms here. So rivers carry sediment, and the big rivers carry a lot of sediment. And if we look at the Mississippi Delta, this is an aerial photograph of the Delta area, and you can see the fingers of a river where the sediments are being deposited. If we zoom out a bit further and look at a satellite photograph, you can see how the sediments are being washed out to sea into the Gulf of Mexico by the River Mississippi. And this is one of the larger rivers in the world, and the amount of sediment it carries is really quite amazing. It carries 1.5 million tons of sediment a day. Gravels are carried in the faster currents, and where those currents fall away, the gravels get deposited. Sands get carried and dropped with weaker currents, and the silts and clays are carried out into deep water. And where there are limited currents, those sediments will sink out. And the scale of this is difficult to grasp. This is a geological cross-section through the Mississippi Delta, showing over geological time how the sediments have built up. And you may not be able to see this in detail, but the horizontal scale is 500 kilometers from the shoreline. And it's vertically, there's vertical exaggeration of 20:1. So this wedge of sediments, which have been built up over geological time, is up to 20 kilometers thick. I was saying earlier, a continental crust is a lot thicker than oceanic crust. Well, here's an example of relatively recent sediments giving a thickness of 20 kilometers. And I made reference to geological periods. The lowest period here, the blue sediments, are dated to the Jurassic period. So quite significant geological processes have an effect over geological time. So just going back briefly to plate tectonics, and the other feature that these give rise to, they are, plate tectonics are what moves the plates around the surface of the Earth, but where they collide, you get rocks being folded, faulted, and uplift, as you saw in the Himalayas. So where you've got compression, where you've got two plates coming together, you'll get the rocks folded. And here in the UK, an example of that is the Alpine orogeny, which created the Alps. But here in the UK, the rippling effect of the African plate crashing into Europe, which threw up the Alps, has also given us our hills here in the UK, in particular the Pennines. A different effect happens when plates move apart. And some of you may know that North America and Europe were joined together and a supercontinent until the Atlantic opened up and pulled apart about 60 million years ago. Well, that tension gives rise to what's called normal faulting, where the rocks break apart and then slide down to stretch out. Also, we have shear faulting, where you get a vertical fault, such as the San Andreas fault, where you get two parts of a plate sliding past each other. So these different structural features give rise to the variety of rocks we see around us. And the geologists map these and draw these on maps and make reference to two key features: the dip of dipping strata and the strike. And the strike is at right angles to the principal dip direction. And it's important to try and think of the rocks in 3 dimensions, because you can get some quite complicated structures forming. For instance, if you've got folded rocks, you will perhaps get a block diagram showing this sort of feature. And a geological map will only show that surface expression, those curving rocks on that horizontal surface. So if we look at an example of folded rocks, the Pennines and the Peak District Dome, here you've got the older basement rocks, which are generally igneous, covered by sedimentary rocks. And these are, in the Peak District, carboniferous limestones, shales, and the millstone grit. And then on the fringes in Yorkshire on the one side and Lancashire on the other side, you've got coal measures being exposed. But this uplift has given rise to erosion, and the centre part has been eroded out. So you've got older rocks, the older limestone, being exposed in the White Peak, and the gritstone occurring around the edges, such as at the Roaches in Staffordshire or Froggatt Edge near Sheffield on the eastern side. And further north, you've got that gritstone cap creating features such as Kinder Scout. So this gives rise to another aspect of folding rocks. Different rock types have different brittleness. If we look at gritstone, a very coarse sandstone, instead of bending, it will crack. And that cracking will give rise to jointing, which is very evident, as you can see here at Froggatt Edge. Also, the same brittleness is seen in limestones. So instead of gently folding, where the crust is buckled, these types of brittle rocks will crack. The same is not true for shales or mudstones. These will just bend, and you'll often see flexed rocks in in cliffs or in seaside um, cliff faces. Occasionally, you'll see sedimentary rocks laid over an erosion surface. At one point, these rocks the lower rocks were clearly dramatically folded, but then were eroded off, and then that erosion surface was subsequently reflooded and covered by sedimentary rocks again. And that gives you what's called an unconformity. One of the other features of glaciation, which I didn't mention, is that during ice ages, a lot of the ocean water is caught up or trapped within the ice caps, and that gives rise to sea level falling. So during the last ice age, Great Britain was joined to Europe, and sea levels had dropped by up to 200 meters. So the Atlantic Ocean was actually only um, um, coastline was only present at the edge of the continental shelf. And it's that changing sea level that gives rise to these unconformities. Now let's move on to a little bit more about rocks. Igneous rocks fall into three different types. Iron-rich basalts, such as are produced in mid-Atlantic ridges, as we saw in Iceland. And when the Atlantic Ocean first opened, we had extensive basalt eruptions around the Great Britain. And these are evident in Western Scotland and in Northern Ireland, such as at the Giant's Causeway. We also have large igneous rocks, such as granites, and these are quartz-rich, generally generated by deep mantle eruptions within continental plates. And these granite, so-called batholiths, are present in fact, under the Pennines, but also extensively present within Cornwall and in the Cairngorms in Scotland. Very hard but brittle rocks, which again give rise to jointing. The third category of rocks are of igneous origin are the volcanic ashes. And a good example of that would be the rocks of Snowdon, which are made up of ash, but when it's solidified and indurated, we would call that a tuff. And tuffs are often used as a very convenient building material. You can cut through it and make blocks for building. And this is an example of volcanic ash, a tuff, where you can see the darker rocks are volcanic bombs which have been trapped within the ash deposits. So those are igneous rocks. Let's talk a little bit about sedimentary rocks, because a lot of our work in the near surface geology will be these drift deposits, unconsolidated or superficial deposits of sediments, of soils, in other words. And at the coarse end of the scale, we have gravels. River gravels, these are typically rocks which have not travelled all that far, so they are often platy or elongate. But if they've come down to the shore and deposited in the sea along the coast by coastal coastal drift, then they will be rolled up and down the beach, and you'll get much more rounded gravels, such as you see here on this Torn beach. And those ostensibly very similar, but they will have slightly different permeabilities, as you'll see in a moment. Finer grained sediments include beach sands, but also wind-blown sands. In my early career, I spent some time employed mapping the Namib Desert, which is one of the larger and oldest deserts in the world. And all of the deposits, or a lot of the deposits I was mapping, were aeolian deposits, wind-blown deposits. And then finer sediments again include the muds, silts and clays. And these are made up of minerals, clay particles, which are platy and very small. And because of their size, you get interparticle forces being significant. So the coarser fraction are generally known as granular soils, and the finer fraction, the silts and clays, are known as cohesive soils, because that cohesion is created by those interparticle forces, forces of attraction. So what were sediments over geological time can be formed into rocks if those sediments are buried under thicknesses of overlying sediments, as we saw in the Mississippi Delta. And under time, temperature, and pressure, you get sedimentary rocks being formed. So those coarse gravels will form conglomerates. The finer sands will form sandstones or gritstones, as you can see here in the roaches, or finer sands again. These are the Triassic sandstones, Sherwood sandstone present in Cheshire at Beckforton. And then the finer sands, finer sediments again, will give you mudstones and siltstones. And often, because of changing sea levels, you'll get sequences of mudstones, siltstones, and in the Carboniferous, extensive areas of swamp vegetation will create holes. And that sequence of coal, mudstone, siltstone, and occasional sandstone layers repeat themselves in what are known as cyclotherms. Then the third type of rock are metamorphic rocks. And these are, they may be igneous rocks, which have been recrystallized through temperature and pressure, but are more dramatically characterized by sedimentary rocks, which have been deeply buried and recrystallized through temperature and pressure. So at one end of the scale, you get things like coarse sandstones and with banding being recrystallized into what's called gneiss, where the quartz minerals relocate into quartz-rich bands, and the clay minerals will relocate into the darker bands. So this is a photo of Lewisian gneiss from Scotland, and you've got a very dramatic folding and unfolding of what was a semi-viscous rock before it recrystallized. Finer sediments, such as extensive mudstones and siltstones, will be recrystallized into slates. And this is a photo of one of the slate quarries at Dinoric in North Wales. And The feature here is that the recrystallized clay particles will realign and give you a very clear and distinctive cleavage. So you can split off thin rock layers into slates, used for roofing, of course. Okay, moving on, let's talk a little bit more about sediments from a point of view of permeability. Sedimentary beds have a very distinctive feature of having a fining upward sequence. The coarse fraction will fall out of the water flow first, and then you'll get this fining upward from grits to sands to fine sands to silts and clays. And schematically, this is what you get. And each bed will have this sequence, which gives rise to a very clear and distinct characteristic of permeability anisotropy, where the coarse fraction will have a significantly greater permeability in the horizontal than the vertical permeability. But in terms of measuring grain size, geotechnical samples will be taken to a geotech lab, and the sediment will be weighed and then sieved through finer and finer sieves. And the weight is then plotted on a log graph, such as you see here, which will be described as a particle size distribution curve. So a glacial till, which will have a range of a wide range of sizes from clay right through to gravel, will have a more elongated curve, as you see here. A beach sand where all the sand is of the same or similar size will give a much steeper curve. Again, illustrated on the graph. And these curves describe properties that are very important for us, because porosity and permeability and grain size distribution determines permeability of a soil. So here's two types of soil: a clean, single-sized, high porosity, single-sized sediment, and a low permeability, low porosity, where all the small spaces are filled up with a smaller sediment. So this gives rise to a nomenclature issue. As geologists refer to the left-hand side as being well sorted, and for the right-hand side, poorly sorted, because there's a wide range of grain size. On the other hand, engineers will term the left-hand one as poorly graded, and the right-hand one well graded. So depending on who your audience is, be very aware that these have very different meanings. And I made reference to the rounding effect. Sediments which have been travelled a long way will be more rounded than sediments which have just been released from a rock mass, and which will be much more angular. And the angularity, or the degree of rounding, will give increased porosity as you move to the right. And permeability, which is slightly different measure, is determined by the interconnectivity of the pore spaces. And that generally, again, will be increasing as you move to the more rounded, more travelled sediments. So let's move on to permeability in a little bit more way, and how gases move through the ground. And gases travel through the ground by three drivers. You have advective or pressure-driven flow, or diffusion, where gases from areas of high concentration move to areas of low concentration. Both of those occur in the unsaturated zone above the water table. But we also have different gases going into solution and being carried in the groundwater. And clearly this happens below the water table in solution. In terms of permeability and gas flow, hydraulic conductivities is often referenced as a key factor. And this is shown on this scale here. Clean gravels and measured as meters per second. You'll have clean gravels having a K value of 10 to the minus 1 at the one end. Unfissured clays at the other end may be 10 to the minus 10 meters per second. Put that into practical terms. This is a diagram showing how a tank with a meter of sediment filled with water will drain away through a tap. If it's gravel, it will drain away in 2 minutes. Sand will take 20 minutes. A silt will take 2 hours, and a clay may take up to 2 days. So that gives you the range of permeabilities for those different sediments. Just a point of caution, note that K can be quoted in different units. Instead of meters per second, it may be meters per day. And in the States, the United States, they will use different measures again, non-SI units. So in terms of permeability and the ability of ground gases to flow, we've got something else to think about. A lot of published data refers to hydraulic conductivity, and this freely available guide on permeability indices of a lot of our rocks and soils in the UK is published by the BGS. And one of the tables or boxes within that publication talks about Darcy's law and the very simple equations linking hydraulic conductivity to hydraulic gradient and the flow of water through that sediment. But unfortunately, gases are not water. So hydraulic conductivity isn't the right parameter to use. What we need to use is intrinsic permeability. And this is the permeability of a rock or of a soil independent of the fluid properties. So a slightly more complicated equation is needed, which takes into account the density of a liquid and the viscosity of a liquid. And in terms of, or just as an aside, looking at permeability, hydraulic conductivity, this is a table again from our publication showing the range of published data for standard different soil or rock types. Point is that water and air have different viscosities, and air is 100 times less viscous than water, which means that it will travel faster and further, or has the potential traveling faster and further through permeable rocks than equivalent water contaminant. In terms of drivers, this bit of research by Ettinger and Kerfoot, published in 2012, describes a comparison between the different fluxes for different drivers for 3 different soil types: sand, silt, and clay. And the point to make here is that in granular soils, in the coarser fraction, in sands, pressure-driven flow is 1,000 times more significant than diffusion. Even in lower permeability soils such as silts, pressure-driven flow is significantly more um, uh, uh, dramatic than diffusion. It's only when you get into low permeability soils, such as clays, that diffusion becomes the dominant driver. A different bit of research looking at published by Massman and Ferrier, going back to 1992, where they carried out 2D finite element analysis of a 25 millibar pressure fall over a 24-hour period. And in fine, relatively low permeability soils, such as silts, that pressure fall would allow gases to migrate 11 meters. In a fine sand, gases would move 25 meters. And in a medium sand, it would move up to 45 meters in that pressure fall in that period of time. I made reference to permeability and isotropy, and that has a profound effect on the results we take from monitoring wells. As you may know, monitoring wells are constructed within boreholes sunk vertically through the soils and rocks. And but the point is that they only pick up ground gases that are migrating laterally. But most developments new developments we are concerned with will be built on the surface and only be subject to vertical migration of gases. And that means that in most cases, or a lot of cases, we are providing conservative risk assessments. We will be overestimating the hazard that the new development will be exposed to. Unfortunately, there's a significant caveat to that, and that is where a site is, or site geology is changed after the site investigation or monitoring phase by the site being re-profiled, levels changing, or deep service trenches being dug and which cut through those sedimentary layers. Those sorts of changes can introduce preferential migration pathways. Not forgetting monitoring wells themselves, if they are located under the new building, they themselves will provide a preferential pathway for migrating gases unless they are over-drilled or grouted up. And the results of gas migration can be significant. Many of you will be aware of the Losco event in 1986. Landfill gas migrated into the subfloor void of this residential house, which was completely destroyed by an explosion. This was a catalyst. This event was a catalyst for a lot of guidance documents being written. But it's not a UK, limited to the UK. Things happen all over the world. I spent a lot of time in Australia providing training to Australian professionals. And one of the events there was the Cranbourne event in 2010, where landfill gas hadn't been properly managed, migrated through jointed basalts under this housing estate. And more recently in the UK, the Gorebridge incident in Scotland, where a whole housing estate was affected by, in this case, mines gas, and had to be demolished, and GGS are currently involved in the rebuilding and monitoring of the rebuild. So just a few slides, final slides. Just remember that those the permeability of rocks is largely determined by fissure flow through those joints or fissures. And those can give rise to quite dramatic permeabilities, bulk permeabilities, even through what are sometimes considered to be impermeable rocks. So finishing off, talking about visualizing the subsurface. geology is really fascinating when you can see it in 3 dimensions, as you can see here in this sea cliff. But most of the time, we are facing a site like this, nice open field or brownfield site, and all we can use as a tool to understand what the underlying geology is a borehole and a borehole log. So interpreting logs, which are very discrete vertical samples through a site, and trying to translate that into a 3D model takes quite a lot of mental agility. But the main tool for presenting this information is our conceptual site model, where we pull together all the available information, published geology, borehole information, monitoring data, and put it into a schematic image that will allow us to, understand the relationship between a gas source, a gas migration pathway, and a receptor. Apologies, this is a slide which is slightly out of kilter. So conceptual site models need to be site specific, where you identify the key features on a site and identifying the key migration pathways which may occur, as you see here. Different sites have different characteristics which need to be understood and described. And the best way is some sort of schematic drawing. The site-specific nature of this is really, really important. So that's the end of my Geology 101 for ground gas contamination. I'm happy to take some questions. I'm slightly up to the hour, but I'll be very happy to take questions. Just one final slide. Have a look at our website. We've got a whole program of other webinars throughout the year. In addition, we've got face-to-face training happening in a number of places and a number of dates. Visit our website to see the latest information on that. Thank you very much. Over to you, Louis.
Thank you so much, Simon. Yes, very interesting. And as Simon said, a lot of exciting webinars this year for 2025, and you can find them all on the website. But let's get to the questions. So just quickly, someone asked if they can have a copy of the slides. So yes, with the free webinars, we'll be posting recordings as usual on our YouTube channel. So you can find them there. And then a question for Simon. On preferential pathways, should monitoring wells be positioned outside of proposed building footprints as best practice?
Where possible, if you know what the master plan is of where your new development's going, it's always best to relocate or locate your monitoring wells outside a footprint of buildings. Some of the earlier guidance documents failed to point that out. But yes, best practice is locate them outside a footprint. But if you don't know where the final development's going to be, then those monitoring wells should be effectively removed or sealed, over drilling and grouted up.
So much. And then we have a question. What is the worst type of ground gas that could be found in a property?
Well, I haven't discussed ground gas hazards, but the most dramatic is an explosive risk, and that can arise from explosive concentration of methane or hydrogen. Hydrogen is less common, but is is generated or can be generated from slag deposits. Methane, though, is a principal constituent of landfill gas. It's present at source at concentrations of 60% methane, 40% carbon dioxide. But the explosive range of methane is much lower than that. It will be explosive in the range between 5 and 15% by volume. And if that comes into the house, like we saw in Losco, then that is a very real hazard that unfortunately has been realized in a number of occasions. The second most common hazardous gas is carbon dioxide, which is an asphyxiant. Again, it has killed people and kills people very quickly within a few seconds of being exposed to high concentrations. I should also say that both methane and carbon dioxide are often associated with abandoned mine workings, and where um, these are present beneath a new development, then that is a real hazard that needs to be investigated.
We do have a webinar on mines, drilling, and grafting risks this year, don't we? So could deep dive into that one as well there. And then Steph is asking what the best practice to monitor vertical migration of ground gas is.
If you want to, monitoring wells are a standard tool, scientific instrument, I'd like to think of them as, and they need to be carefully designed and constructed. But those monitoring wells, vertical monitoring wells, will give you that horizontal permeability. The only way of getting an accurate handle on what the vertical permeability is by either doing surface emission survey, which is very cost effective to identify surface emission locations. And then once those are located, doing a flux box test on those locations. Flux box tests are very well written up in Environment Agency guidance. Unfortunately, they're quite expensive to carry out, and you need a fair number to be statistically valid.
And then we have a question from Phil. Could piling foundations create a preferential pathway for ground gas?
There's a lot of simplification of a problem written up about piling. Piling can, in its simplest form, where you've got a vibropile, single-sized stone column being driven into the ground, those will give you a very definite preferential vertical pathway right up under the building you're building. Other piles, such as cast in situ piles, are probably not a problem because any of the permeability will be sealed by the concrete flowing into the surrounding soil, the annulus. But the halfway house where you've got a concrete driven pile, those driven piles will get a certain vibration or whiplash, causing an annulus to form in the top third of the depth, and that annulus will be significant, particularly if it's an end-bearing pile driven to a harder strata. And that annulus, again, can provide a vertical migration pathway.
Perfect. Should we do two more questions? And if anyone has any additional questions, do feel free to drop us an email. But I'll just pick two. Andy's asking how long do you determine that gas monitoring should be undertaken for sites? where housing developers will be constructing new homes? Is there a specific time frame?
Well-established guidance, um, Syria C665, or more recently, you've got British Standard 8576, which gives some thoughts on period of time. What I would say is you need to do sufficient monitoring to give you confidence in the results you are interpreting.
Mhm.
So if there's uncertainty, you need to do either better quality monitoring through, for instance, continuous monitoring, or do a longer program of spot monitoring, periodic monitoring, to give you the confidence on the conclusions you're drawing. I would say guidance is guidance, and it needs professional judgment.
Perfect. And then the last question is a question about radon, and how far from the source does it travel? Um,
Radon. Radon is a special case, really, because it is a radioactive decay product from uranium. And unfortunately, uranium is present. Well, originally, the highest concentrations of uranium were found in granite rocks, but granite rocks weather, as I've described. You have sediments being formed. Those sediments will contain weathering products from granite rocks. As a consequence, all rocks and all soils within the United Kingdom will contain uranium at various concentrations, which means that you'll find radon in every household in the country at background levels. The difficulty is measuring the site-specific concentrations within a particular building, because how that building is not only constructed, but how it's used will determine concentrations you'll find in it. If you've got a young couple who like fresh air and have the windows open most of the time, you'll get very low concentrations of radon. An elderly couple, or a more cost-conscious family who want to keep their houses warm and don't have ventilation, they will have the same, even identical houses, but that latter cost-conscious family will have higher radon concentrations in it. So it's not about sources, it's more about house design and how a house is, or a dwelling is used.
Interesting. Okay, that's it for questions. I've had a couple of questions about different resources and stuff that you mentioned. And yeah, like we said, just drop us an email, and we'll get back to you. But thank you so much for the brilliant webinar as always, Simon, and for everyone and their great questions.
Thank you, Louis, and thank you everyone for listening. I look forward to having you register for one of our future webinars. So bye for now. Cheerio.